Bismillahirrahmanirrahim. Assalamu alaikum. So let's start the last topic for three-phase AC machines, which is induction generator. If an induction machine is made to run at synchronous speed, now this can be done by coupling a prime mover with an induction machine. Initially, the induction machine is started as a motor. When it attains speed close to the rated speed, the prime mover coupled with the induction machine is made to produce torque in the same direction as that of the direction of rotation of the induction machine. This will increase the speed of this set, of this induction machine prime mover set. A figure below shows this discussion. This is the power system to which the induction machine is connected and is running previously as a motor. We have coupled a prime mover, a source of mechanical energy, with the induction machine, which is turning in the same direction with the help of this couple as that of the direction of rotation of the induction machine while it is running as a motor. Now when it attains a speed close to the synchronous speed, we will open this steam inlet valve. This steam will expand in the turbine and it will produce torque. Since both the turbine and the machine are running in the same direction, by increasing the steam input, the turbine will produce more and more output that will increase the speed of this couple of this set machine, induction machine turbine set, and ultimately we can attain the result that NR is equal to NS. Now as the induction machine is running at a speed NR equal to NS, the relative motion between the rotor and the stator revolving field is zero. It means that the rotor induced EMF, rotor current and slip will be zero. Induction machine in this particular condition is neither working as a motor nor as a generator, and it is said to be floating on the system. In this condition, the machine is drawing only such amount of current from the system which is required to maintain revolving magnetic field in the stator, and that is required to supply the copper losses and iron losses in the stator in this condition. Iron losses means the core loss in the stator, while the rotational loss, that is the friction and windage loss specifically, is supplied by the prime mover. Now if the speed of induction machine is increased further above the synchronous speed by increasing the prime mover input, that is in this particular example by opening the steam inlet valve further, the relative motion will now be in the clockwise direction. Just see this figure. The synchronously rotating field is rotating in clockwise direction and S direction is shown. Now from the previous discussions of the torque production in induction motor, we know that the rotor rotates in the same direction as that of the direction of rotation of the rotating field. However, NS is less than NR for induction motor operation, and we have already discussed that the direction of relative motion for the induction motor case will be opposite to that of the direction of rotation of the synchronous field. However, in this case, since we have increased the rotor speed above the synchronous speed, NR is larger than NS, we can see from this figure that the direction of relative motion is now clockwise. Now using right hand rule, we can find the direction of the voltage induced and current flow. The first finger points in the direction of the field, which is upward in this case. The thumb points in the direction of rotation, which is clockwise. Then the second finger will point in the direction of voltage induced and direction of current flow, that is out of the paper in this case. In the if we compare it with the figure on the next page, while the machine is running as a motor, just see that this figure has been reproduced here. Initially the machine was running as a motor, NR was less than NS, so relative motion is clockwise. From the right hand rule, the direction of voltage induced, the direction of magnetic field given by the first finger, the thumb pointing in the direction of relative motion, that is counterclockwise in this case. Then the second finger is pointing in the direction of voltage induced and current flow. Then we applied left hand rule, that is for the torque production the conditions were satisfied. Again, first finger pointing in the direction of field, the second finger is pointing in the direction of voltage induced and current flow, and the thumb points in the direction of the rotation or the direction of force, that is clockwise in the same direction as that of ns. This is the brief discussion, the production about the torque production in induction motors. Now just see here that the current direction is into the taper in this conductor. As compared to this case, when we come back to this figure, we can see that the voltage induced and current flow direction has now been reversed because the direction of relative motion has been changed. Now it is clockwise. So the direction of voltage induced and current flow has been reversed. It is now out of the paper. So since the direction of current in rotor circuit has been reversed, we can show it with the help of this red arrow. The blue arrow shows the original direction of current in rotor when the machine was operating as a motor. When NR becomes larger than NS, the relative motion direction reverses, so the direction of current in the rotor circuit also reverses. While the machine is running at a speed larger than ns, the slip will become negative. So while the induction machine is working as a generator, its slip will be negative. Now using this negative slip or this negative sign of the slip, we can see that the air gap power is also negative. What it means? It means that the direction of power flow has been reversed in the air gap. Initially, the power flow direction was from the stator. The power crosses the air gap and it is induced in the rotor. Now the reverse will happen. Power flow from the rotor through the air gap, across the air gap into the stator, and from stator towards the electrical loads. Thus direction of real power flow has been reversed. However, the machine will keep on drawing magnetizing current from the power system to which it is attached. The reactive power flow direction will not change. It is drawn by the machine from the system. The reason for this is that an induction machine requires revolving magnetic field for its operation, as we have already discussed in different lectures, in different previous lectures. So if revolving magnetic field is absent, how would the voltage would be produced? There will be no voltage. As we can see from the last figure, that if there is no revolving field, there will be no voltage in the rotor conductors and hence no current flow. Now since there is no field circuit in induction machines like we have seen in DC machines. What is a field circuit do? A field circuit produces magnetic field. It is a source of magnetism. It is a source of producing magnetic field in a machine. So in an induction machine, there is no proper field circuit. So an induction machine cannot have a revolving magnetic field produced by its own sources. An induction machine requires magnetizing current from the power system to which it is attached, that produces revolving magnetic field, which is necessary for the operation of machine as a motor as well as a generator. So as there is no field circuit in an induction generator, its voltage and frequency cannot be regulated. We will discuss this regulation, the regulation of voltage and frequency in detail in synchronous generators, inshallah. For time being, just try to cope it with, or just try to go through with it, that in the absence of the field circuit, the voltage and frequency of a generator cannot be regulated. The frequency and the voltage of the induction generator will be the same as that of the voltage and frequency of the system to which it is attached. Now this feature is very useful in the application of induction machines to be used with windmills in cogeneration operations. In windmills, the varying speed does not vary the output frequency. Since the wind speed cannot be regulated, so the speed of windmills varies. So the varying speed of the generator will not change the frequency of the output. As compared to induction generator, the other very common or very popular type of the generator is synchronous generator, in that machine in synchronous generator, with the variation in speed, the output frequency also varies. In induction generator, the variation in speed does not vary the output frequency if it is connected with a large power system. So this feature is very useful for producing electricity in varying speed conditions, that there is no fancy equipment or instrumentation is required to regulate the frequency in an induction generators. As the speed of the machine is above the synchronous speed is increased above the synchronous speed, the relative motion will increase, or the slip speed will increase. In other words, this will increase the induced voltage and current flow. Thus, power output will increase from the generator. Larger the current I2, larger will be the air gap power, which is will cross from the rotor to the stator and is supplied to the system to which the generator is attached. The figure on previous page, on the page number 85, for NR larger than NS, the conditions for torque production in this machine have also been satisfied. What are the conditions? There should be magnetic field, there should be a current carrying conductor placed in it, then it will experience a force. Now just see the figure on that page. The first finger points in the direction of the magnetic field. The second finger points in the direction of voltage induced, in the direction of current flow. The second finger points in the direction of current flow. Then the thumb will point in the direction of force or the direction of torque produced, which is counterclockwise. So it means that the induction machine, while it is generating, will produce a torque opposite to the direction of rotation. That is negative torque. Larger the N or above the Ns, more is the relative motion, larger is the power output, and more is the negative torque. And with the help of this information, we can draw the torque speed characteristics for an induction machine, a complete torque speed set of characteristics for an induction machine. We are familiar with the plugging or braking region, motoring region. Here the slip is larger than 1, here the slip is between 1 and 0, and here we have seen that the slip is negative. So this is the section of the torque speed characteristics for an induction machine while it is generating region. So this will continue until the maximum negative torque is produced by the machine. After that, the output of the generator will drop, resulting in overspeeding of the generator, because in this case the load torque will decrease because the generator will not produce a power more than this value. So the torque supplied by the prime mover will increase, because it was supplying a power which was sufficient to maintain this much negative torque. So in this case, the generator will overspeed. So let's go through an example. We have a 3-phase 6-pole 415 volts 50 Hz induction motor rated at 15 horsepower and speed 985 rpm. It is driven by a turbine at a speed of 1015 rpm. The equivalent circuit parameters are also given. You have to determine the active power that the motor will produce while it is driven as an induction generator. Now, how can we claim that the machine is running as an induction generator? We can claim it from this speed. For 6-pole machine, the synchronous speed is equal to 1000 rpm. Since the given speed at which the turbine is driving this generator is larger than synchronous speed, it means NR is larger than NS. So this machine is acting as a generator. We can calculate the slip, which is negative. We can calculate the rotor circuit impedance Z2. We can calculate the forward impedance ZF, and we can calculate the equivalent total impedance Zin. From here we can calculate the stator current I1, and we can calculate the apparent power S. It is equal to 3 times V phase the phase current conjugate. So this is the answer here. You can see that the power is with negative sign. This negative sign shows that the direction of power flow, real power flow, has been reversed. Instead of consuming the real power, now the induction machine is supplying the real power to the power system to which it is attached. And you can also see that the direction of reactive power flow is same. It is with positive sign. It means that still this machine is drawing reactive power from this system to maintain its revolving field. Isolated induction generator operation. If the induction generator is not connected with any power system, it has to operate alone like a backup generator in case of electricity failure. This is known as an isolated operation. So an induction machine lacks a proper field circuit in order to build up voltage. Capacitor bank should be connected across its terminals as shown in the figure below. We have an induction generator, and across the terminals of the induction generator we have connected a capacitor bank, and this set of induction generator and capacitor bank is supplying some load. Now capacitor bank, as you may note, are connected in the capacitors are connected in delta in low voltage systems. The reason for this is that the line voltage and phase voltage are same in delta connection, so it results in 3 times larger reactive power production as compared to star connection. Since the line voltage will remain same in both the configurations, delta and star, let's calculate the reactive power while assuming that the capacitor bank is star connected. It is Q is equal to V square by XC, or phase values are given. Now in star, the phase voltage is line voltage by under root 3. From here we can conclude this relation. Now just calculate the reactive power per phase for delta connection. Again, the per phase voltage square divided by the reactance, resistive reactance at C. In delta, line voltage and phase voltage are equal to each other. So equating these two, line voltage square by XC, line voltage square by XC, so we can replace this term by Q delta, and you can see here clearly that Q delta is 3 times Qy. It means that capacitor bank, while it is connected in delta configuration, will produce 3 times the reactive power as it is produced while it is connected in star connection. Now, when an induction machine is made to run at a speed larger than the synchronous speed, that is Nr is greater than Ns at no load, the residual magnetism in the rotor core will cause voltage to be induced and hence current flow on the stator side and the capacitor bank attached across the stator terminals. Now note that if there is no residual magnetism, if the generator has lost the residual magnetism, then it will never build up voltage. What is the solution to this problem? You have to switch on a capacitor bank with some residual voltage, or you have to run the machine briefly as a motor. This will be sufficient enough to build up the flux in the induction machine rotor. Now as the slip is quite small, R2 by S will become very large, so rotor branch can be neglected and the circuit will reduce to this form: stator side resistance, reactance, and the magnetizing branch reactance. And since we have connected capacitor bank across the induction motor terminals, induction machine terminals, so the capacitance connected across the terminals is also represented here. Now this current flow in the capacitor bank due to the voltage induced by a residual flux will increase the voltage, which further increase the capacitive current until rated output voltage is attained. This process of voltage buildup is shown in the figure below. Just see this figure. There are two curves. One is the magnetization curve, this one. This is the magnetization curve. This other one is a capacitance line. This is the capacitance line. The point of intersection of these two is the operating point. Magnetization curve can be plotted by running the induction machine as a motor at no load and plotting the applied voltage versus the current drawn as the voltage is increased gradually from 0 to the rated value. Non-linearity of the curve is due to the saturation of the stator and rotor cores. The capacitance line and the circuit for this is shown here. This particular circuit is for the plotting of magnetization curve. Note that since the machine is operating at no load, the rotor side impedance is ignored. We can ignore the circuit. It will come to this simplified form, or even more simplification can be obtained by eliminating this branch as well, so that we can assume that simply source is connected directly across the shunt branch JXM. How can we plot the capacitance line? This circuit will help to understand us this circuit will help us to understand the plotting of the capacitance line as shown in the topic below. The capacitance line is a plot of the voltage versus current of the capacitor when measured alone. We will separate out the capacitor and we will measure the voltage versus current for a capacitor. Then for the capacitance line shown, V is equal to I XC, where XC is the slope of the line. The slope of the line is XC. So you will increase the voltage, the current will increase the voltage, current will increase. So the slope of this line is XC. Now installing capacitor bank across the generator terminals referred to the figure. The voltage V naught due to the residual flux causes I naught current in the capacitor, as you can see here. Due to residual magnetism, voltage V naught will be produced. A voltage V naught will be produced due to residual magnetism that will produce a current I naught in the capacitor. This current I naught also appears in the XM branch, as you can see in this simplified figure. For understanding, this figure has been further simplified by ignoring this branch R1 and JX1, that the same current I naught in the capacitor will also pass through this reactance XM. So I naught also appears in XM, which as indicated on the magnetization curve causes the voltage across it to rise to V1. You can see from this figure that the current I1 in the magnetizing reactance, I naught in the magnetizing reactance, the current I naught in the magnetizing reactance will rise its voltage to V1. This voltage V1 also appears across the capacitor and causes a higher current I1 to circulate, which increases the reactance voltage to V2 and so forth. So this process will continue. The point of intersection of the magnetization curve and the capacitance line is the no load operating point of the generator. Although the process is described as a step process, actual build-up is a smooth and rapid rise to the operating point. Adjustment of the no load voltage can be done by changing the slope of the capacitance line, as XC is the slope of the capacitance line and XC is 1 by 2 pi FC. By increasing the capacitance, the slope XC can be decreased. While the slope is decreased, it increases the voltage, as we can see from this graph. The magnetizing current, the voltage. So we have the plot for 3 different capacitances, in fact 4 different capacitances. If we want to increase the voltage, we will increase the capacitance, it will increase the voltage, because the slope will decrease, XC will decrease as we will increase the capacitance. So as the slope XC is decreasing, so the out voltage from the induction generator is increasing. There is another capacitance which is shown here and is termed as critical capacitance. This particular capacitance is the value of the capacitance that causes the capacitance line to be tangent to the magnetization curve. Voltage will never build up for capacitance value below the critical capacitance. How can we calculate the frequency of the output in no load condition for an isolated generator, as XC is the equal to V operation, no load operating voltage, divided by no load operating current, as we can see from the previous figure here, that VOP is basically the no load operating point voltage IOP is the no load operating point current. So XC is the operating point divided by I operating point. XC is 1 by 2 pi FC. So by rearranging this equation, we can calculate the frequency at no load. When the generator is loaded, its voltage will rapidly fall, especially for lagging power factor loads. For reactive loads, for example, an induction motor is started on induction generator. This is shown here. While the generator is loaded, its voltage will decrease very rapidly. It occurs because the capacitor bank installed at the induction generator terminals has to supply the reactive power to the generator for producing revolving magnetic field, as well as to the load. If we are trying to run a reactive power load having lagging power factor across the induction machine or across the induction generator terminals, definitely a lagging power factor load requires reactive power for its operation. So the capacitor bank that was previously supplying reactive power only to induction generator for establishing revolving magnetic field in the induction generator has to supply the reactive power to the load as well. So it means that the magnitude of reactive power supplied to the generator will decrease, since the reactive power supplied by the capacitor bank is now divided in two portions: one which is going to the generator for producing revolving field, and the other portion which is going to the load. So it means that the output voltage will decrease with the output voltage will be decreased with the increase of the load. So voltage can be maintained by increasing the capacitance, as we have just seen in the previous plot, that if we want to increase the voltage, what we will do? We will increase the capacitance, it will decrease the slope, that is XC, and we can increase the output voltage from the generator if its voltage decreases by increasing the load. So this concludes the induction generator topics. This concludes our chapter about the induction machines as well. Thank you very much. Assalamu alaikum.